Welcome to Lecture 28 of Math 2213. So what we're going to do today is we're going to continue along with some of the ideas that we introduced last Wednesday, having to do with the expected value and the variance of a linear combination of random variables. In particular, today we're going to focus on linear combinations of means of random variables and totals of random variables. And the most important theorem we'll look at today is called the central limit theorem, which we'll get to in a minute. After we talk about the general statement of the theorem, I'll try and explain some of the ideas behind it and give you some examples of how it can be used. You will have seen the central limit theorem in this past week's lab as well, so hopefully today's lecture will give you a little bit more of an understanding about how it works. So we'll do an example involving guessing the weight of some candies, and we'll look at an example problem or two. So to start with, let's remind ourselves what we were looking at last week, and then we'll state the central limit theorem. This is in section 5.4. So in the last lecture, we saw some results for the expected value of a random variable y and its variance, where y is a linear combination of n random variables, x1, x2, x3, up to xn. So we can write y as a1 x1 plus a2 x2 and so on plus an xn, where the constants a1, a2, up to an are chosen by some method. So last time, toward the end of class, we saw two important special cases, one in which the a's were all equal, and they were equal to 1 over n, and this gives you that your y random variable becomes the average of these n random variables, because you're adding up n of them and then dividing by n. Another important special case is one in which all the constants are 1. That gives you a total, because you're just adding up each of the individual random variables. So the results we wrote down last time about the expected value and variance and distribution of that sum already cover what I'm going to write down now, but it's sufficiently common that I'll write down a sort of a special version of this that deals with the case in which you do have either an average of random variables or a total. So here's the special case. So let's suppose that x1 through xn are n independent and identically distributed random variables. And as a footnote, one way that you can actually get this to happen is if the n random variables represent a random sample with replacement from a population. So that's one way you can get independent and identically distributed random variables. So let's suppose, for example, that the expected value of xi is mu, and the variance of xi is sigma squared. Now you'll notice that there's no I subscript here. That is, the mean and the variance do not change between the different random variables. All of the mu's are the same. And the reason for this is that part of the assumption that we're making is that we have identically distributed random variables. Identically distributed means that they have exactly the same distribution. They have the same expected value, the same variance, and in fact the same probability density function as well. So the means have to be the same. That doesn't mean that the x's are actually equal to each other. It just means that they have the same distribution. They're sampled from the same distribution. So the identically distributed part is really what's giving us that all the mu's are equal and all the sigma squareds are equal. So now we can define our average of these random variables as x1 plus x2 plus up to xn divided by n, and the total as just the sum of the x's. You can also write that as n times x bar. Then the expected value of this random average is going to be mu, and the variance of this random average, the variance of x bar, will be sigma squared over n. That is, it's equal to the variance of one of the individual xi's divided by n. The expected value and the variance of the total are given on the right here. The expected value is n times the expected value of an individual observation, and the variance is n times the variance of an individual observation. Now we can derive these formulas from the general case that we did last time, but I won't go into that again. Now, in addition, if we have that each of these random variables is normally distributed, so the part that's new here, that's different from what was above, is we're assuming that the xi's actually come from a normal distribution, then in fact we can say that the average of the random variables will also be normal, and the total will also be normal. They'll still have the same expected value and variances as above, but in addition now we can say that we know what the distribution is. So if you sum up a bunch of normal random variables, you get another normal random variable. So that's handy to know that if you take an average of normal random variables, you'll get another normal random variable. It makes calculations a lot easier. Now, what we're going to talk about now is sort of a more general version of the same theorem that we've just written down. It's called the central limit theorem. And it says basically the same thing, but it makes fewer assumptions about the distribution of the individual random variables that we're averaging. So let's look at the statement of the central limit theorem first, and then we'll talk about how we might understand it. So the central limit theorem says that for any population, as we draw a sample of n objects from that population, and as that sample size n gets large, then the average of those samples, and this can be thought of as a random average because we're going to randomly choose objects and measure them. The average of those will have a normal distribution with mean mu and variance sigma squared over n. That's exactly the same as above. And the total, similar to above, will have a normal distribution with expected value n mu and variance n sigma squared. So as I've written here, this is exactly the same kind of result as above, but if you look closely, you'll see that there are fewer assumptions. The only requirements that we're making now are that the xi be independent from each other and identically distributed. We are not assuming that they are normal. And yet, even though we're not assuming that the xi's are normal, the central limit theorem says that if you take an average of a large enough number of them, or if you sum up enough of them into a total, that total will behave as if it is normal, even if the individual random variables that you're averaging or summing up for a total are not normal. So that's quite a powerful and seemingly somewhat of a surprising result. We'll look at an example here to hopefully give you some intuition for that. So this is an example I sometimes do with an introductory course on math. And I guess if it was closer to Halloween, we could have done this in class perhaps. But in any case, maybe I'll bring in some candy later this term. So the setup is as follows. Suppose I have 100 pieces of candy, which I've actually got a picture of right here. Not all of these candies are shown to scale, but hopefully you get the idea. And I want to know the mean weight of these candies. So in some sense, I have a population with 100 objects in it, and I'd like to figure out what the population average is. However, my problem is that the scale I have is very accurate, but it only goes up to a total of 50 grams. And some of these chocolate bars weigh close to 50 grams. So I can't really do the obvious thing, which would be to take everything and weigh it at once and then divide by 100 to get the average weight. That would be the easy way to do it. Instead, what we're going to have to do is we're going to have to weigh these pieces one at a time. Now I'm a lazy guy, and so I don't want to weigh all 100 of these pieces. So instead, what I'm going to do is I'm going to randomly choose just 5 of these pieces. I'm going to weigh each of those 5 pieces. I'm going to calculate the sample average, and that'll give me an estimate of the average weight of these bars. So that's what we're going to do. And we're going to go through this exercise as if we're actually doing it, just to build up an intuition for what's going on. So what we're going to do is, let's suppose that we sample 5 candies from that group of 100. So we've got a little hard candy of some sort, one of those caramel candies, a raisin, some fudge, and a granola bar. And the particular weights of these in grams might be 6.4 grams, 6.3 grams, 9.7, 10.1, and then 37.4, let's suppose. So if those are the weights of my different bars, I could use those numbers to calculate a sample average, adding up the 5 individual values, and then dividing by my sample size of 5, which gives me an average of about 13.98 grams. So based on this sample of 5 candies, we would estimate that the average weight of these 100 candies is about 14 grams. Now, of course, if you did this experiment again and sampled it again, you might get a different value. Let's try this a few times just to see what happens. So, in this case, we get a 44.5 gram bar, an 8.1, a 9.7, 2.9, and 5.5. And then if we add these up and divide by 5 again to calculate the sample average, we would get a sample average of 14.14. We could do this a few more times. So for example, if my third sample looks like this, I have 4 candies less than 10 grams and then one sort of medium-sized candy at about 25 grams. That gives me an average weight of about 10 grams. We'll do it one more time. And this time we happen to not sample any of the bars that were heavy, and so our average this time is a little bit lighter, around 8 grams. So as you can see, if you sample, depending on which sample you get, you're going to get a slightly different estimate of the average. In fact, it can vary quite a lot. As little, in this case, in these 4 cases, as little as 8 grams or as much as 14 grams for the average weight of the bars. Now, of course, we've now sampled 20 of the 100 bars, so it's getting to a point where we might be better off just weighing all of them. But from a sort of an academic perspective, it might be interesting to say, well, what would happen if we did a whole lot of these samples? If we generated a lot of different samples of size 5, what kind of averages will we get? And so what I'm going to do is I'm going to think about drawing a histogram of the averages that we have. So I've written down an axis here, and we're going to start drawing a histogram. So the 4 values of x bar that we've gotten so far are 13.9, which would be 10 to 12, there'd be a single one there. There'd be one in the 14 to 16 box, which would be there. There'd be one in the 10 to 12 box, which would be here. And then there'd be one in the 8 to 10 box. So our histogram of 4 values looks like that, in fact. But we could imagine repeating this experiment many times. So what will happen if we do 100 repetitions? So if we do 96 more samples, and there's nothing magic about 100 here. The total of 100 samples has nothing to do with the fact that we have 100 candies in our population. It was just a convenient number that I chose. So if we went and collected 100 different samples, we might get a histogram that looks something like this. Maybe before our start, I'll color in the bars that we've got red here so we know where they were relative to the other ones. And then we'll draw our histogram a different color when we add in the extra 96 more samples. So what we're going to be doing here is we're going to repeat the same experiment that we did above, but 96 more times. We're going to sample 5 candies. We're going to calculate the average weight of those 5 candies, and then we're going to add them to this histogram here. So when we do this, we'll get something that looks like this. So now we have a histogram in which we see 100 different values of the sample mean x bar, each one based on 5 observations. And the 4 values that we originally got are sort of in the middle of that, ranging between 8 and 16 or so. It looks like you could get averages as large as 26 and as small as 4 or 5 grams. depending on which candies you selected. Now, this is kind of tedious to do by hand, and I'll confess that I didn't actually go and sample 5 candies 96 times to generate that. What I actually did was I used a computer to do the sampling. So in fact, I weighed all 100 candies, and I wrote down the weights of those, and I used R to sample various different samples of size 5. And in fact, I could do this more than 100 times. So I could tell R, once I have the weights of the candies, I could write a little program in R that would sample 5 candies and calculate their average, and then repeat it many, many times. So instead of doing it 4 times or 100 times, I could do it 10,000 times. If I do that, I get a histogram that looks like this. So there's a histogram of 10,000 different sample averages, each one calculated on a different sample of size 5. And I'll tell you a little secret here. The solid line, or actually the dotted line, is the true average. It's around 12 grams or so. So that's the truth that we're trying to estimate. And what this histogram is showing us is what the behavior is of a sample average of 5 weights. So we're getting 5 random variables, the weight of the 5 bars we sample. We average them together, and this is a random average, and we see it has this shape. And you'll notice a particular feature of the shape, that there's a peak on the left, and then there's a little gap, and then there's another peak and a tail off to the right. If you think a little bit about what might cause this peak on the left, you may have noticed that some of the bars are heavy, and then quite a lot of them are light. And we noticed that when we were drawing individual samples, that sometimes we'd get no heavy bars, and other times we'd get 1 or 2 heavy bars. If you don't get any heavy bars, then your average is going to be quite light. Whereas if you get 1 heavy bar, you're going to get a value probably between 10 and 20, and if you get 2, then you're going to be higher up than that. So one of the reasons for this double peak is the fact that there's some heavy bars and then a lot of lightweight ones. And in fact, that's one of the reasons why this is a challenging problem. Now, I'll sort of come clean here and show you what the whole distribution is. So here's a histogram of what all 100 candy weights look like. So this is really a histogram of my whole population. These are the weights of all 100 candies. And you'll see that there's a few really heavy candies. Those are the bars like the Mr. Big and Kit Kat and Coffee Crisp. There's a bunch of granola bars that are also pretty heavy. And then there's a lot of little candies like the chocolate coins, the suckers, the hard candies that are very lightweight. And what your sample average looks like is going to be influenced quite heavily by whether or not one of these heavy bars turns up in that sample or not. Incidentally, you can calculate the mean, variance, and standard deviation of this population. So the population mean is 12.11 grams. The population variance is 126.5 grams squared, or perhaps more interpretably, the population standard deviation is about 11.25 grams. So I'll just reproduce the plot that I showed you above. Here's a histogram of the estimated mean based on simple random samples of 5 candies. So this is the population from which we're sampling, and this is how the average behaves when we draw a sample of size 5. And you'll notice that the average of 5 tends to have less variability than the original population. And if you look back at the central limit theorem, you'll see that that's actually what it predicts, that the central limit theorem says that the variance of the average should go down as your sample size n increases. We have a sample size here of n equals 5. So a natural question that one might ask here is, okay, is this central limit theorem working? The central limit theorem tells us something about the behavior of this sample mean x bar. It says that the distribution of x bar should have a certain expected value. In particular, it should be equal to mu. The variance should be equal to sigma squared over n, and it should be normally distributed. Well, here's the true value of mu, and you can see that the expected value of all of these averages, that the center of that distribution could well be mu. So I think that first part of the central limit theorem is working well. Is the variance of x bar sigma squared over n? Well, we won't check that exactly, but we do note that the variability in the sample average is certainly less than the variability we see in the population. So if this population has variance sigma squared, then it's quite plausible that the distribution of these averages has a smaller variance sigma squared over n. So that looks good. The third thing that the central limit theorem says is that no matter what the distribution of the individual random variables, that is, no matter what the distribution of the population is, here it's quite non-normal. No matter what it is, if you average together enough values, if n is large enough, you'll get something that looks like a normal distribution. Is that working here? No, not really. We do not have a normal distribution. The blue graph is not close to a bell curve. It has two peaks instead of one, and it has a long tail out to the right. So it doesn't look like a normal distribution at all. So I guess we have 2 out of 3, but the central limit theorem isn't working. Now I guess we shouldn't give up quite yet, because there is some fine print in the central limit theorem. It says that if your sample size is large enough, then the average should start behaving like a normal random variable. So maybe our sample size of 5 isn't large enough. So let's try making our sample size n larger. And for comparison, we're going to try n equals 5 as a baseline, what we've done already. But then we'll also look at a sample of size 10 and another sample of size 20. And we're going to do the same exercise as before. That is, we're going to imagine that we're going to sample 5 candies, get their weight, and then repeat that procedure many, many times, getting many averages of size 5 and get a histogram of those. Then we would repeat the same thing again, only this time we would sample 10 candies and look at their average and get many averages from many different samples and look at the distribution of all of those averages. And then we could do the same thing again for 20. So let's look at what we get. First, this is the graph that we had before, based on samples of size 5. Now, if we go to samples of size 10, we get a graph that looks like this. And what you'll note is that it still doesn't look quite like a normal distribution. There's still a longer tail out to the right, so it's skewed to the right. And there's still a little bit of a peak. A second peak here. So it's not really normal. That is, the central limit theorem is not yet working for n equals 10. Okay, well, let's try 20 then. So here's what happens if I collect samples of size 20. And this is starting to look pretty good. The distribution of averages of 20 candies starts to look quite a lot like a bell curve. It does look like it's centered around the true value. And in fact, we can compare what the central limit theorem says the standard deviation of these means of 20 observations are with what the actual standard deviation of each of these means are. So I have a histogram of 10,000 means here, and I can calculate the standard deviation of those 10,000 numbers. When I do that, the standard deviation of the values in this histogram works out to be about 2.3. Now, according to the central limit theorem, it says that the standard deviation of the sample mean would be sigma over root n. That's coming from the fact that the variance of the average is sigma squared over n, so the standard deviation is just the square root of that. So here I said that the population had a standard deviation of 11 1/4. We have a sample size of 20, so 11 1/4 divided by root 20 is 2 1/2. And so in fact the central limit theorem is surprisingly accurate. It's pretty close here. So the CLT is accurately predicting the variability in the sample mean. So it accurately predicts the standard deviation of x bar. Now you'll notice that 2 1/2 is not equal to 2.3. And in fact, there's a technical reason for this. That in fact what we're doing here is we are sampling without replacement. And as a result, this has a slight effect on the variance. It tends to make the variance of the sample means a little bit smaller than if you sampled with replacement. To see this from an intuitive perspective, if you sampled all 100 candies and calculated their average, sampling without replacement, then there'd be no variation at all because there's only one possible sample you could draw. It's weighing all 100 candies and taking their average. So as your sample size gets bigger, the variance gets smaller a little bit faster than you would expect. But for 20 candies, it's pretty close. So the point here is that the CLT seems to be working. We have a bell curve, it's centered around the population mean mu, and the variance is roughly what the central limit theorem would predict. So the CLT seems to be working here. Now, as I said earlier, this sort of repeated sampling is a bit of an academic exercise. No one in their right mind is going to sit around all day drawing many 10,000 different samples of size 20, weighing the candies each time, and then calculating an average. You just weigh all 100 candies and be done with it. However, what this exercise is doing is it's getting us to think about what might happen if we did sample 20 candies. How much variation is there in a sample of size 20? And the really neat thing about this central limit theorem is that it says it can predict how much variation there will be in a sample of size 20. You don't have to repeat this experiment 10,000 times. Instead, you can use the central limit theorem and it will tell you how much variability you can expect. So the central limit theorem tells us about the behavior of the sample mean x bar under repeated sampling without actually having to generate that many samples. So we can use the central limit theorem to predict what will happen without having to generate many samples. So that's a very powerful result. And maybe before we move on, I'll just recap what the central limit theorem says and talk about it for a minute. So the central limit theorem says that the sample mean x bar will be approximately normally distributed with expected value mu and variance sigma squared over n. So what that means is, on average, the sample mean is a good estimate of the population mean. And we see that above. We see that the distribution of possible x bars you might get is centered around the true value, mu. And the variance of the sample mean is going to depend on how many random variables or how many data values you include in your sample. The larger a sample you get, the less variation there will be in the mean. And this is intuitive. If you want to get a good estimate, you get more data, and you average more data values together. And this is what the central limit theorem is saying. Furthermore, the central limit theorem is saying that if you have a large enough sample, you're going to get a sample mean that behaves like a normal random variable, no matter how crazy and wild the population distribution is. And in this case, we had quite a different population distribution. The 100 bars had a distribution that looked very non-normal, but once you sample 20 bars and average their weight, or 20 candies I should say, you get something that's quite close to normal. So this is a nice result. So what I'm going to do now is I'm going to look at an exercise that shows how we can use the central limit theorem to solve a probability problem. So here's the question. Suppose that we have a stationery store and we're selling a bunch of different things, including pencils. And we collect data on how many pencils we sell every day. And we find that a Poisson distribution might describe the number of pencils sold. Remember, a Poisson distribution is a distribution that describes a random variable that can only take positive or zero values, positive integers. or non-negative integers. So that's perhaps a reasonable model. And let's suppose that it can be described by a Poisson distribution with parameter lambda equals 5. How many pencils should this store have in stock for a month, 30 days, if they want the probability of selling out to be 1%? So this is an application of the central limit theorem, although it may not immediately look like it at the beginning. So let's think about first what this Poisson distribution means. If we have a Poisson random variable, so if we say, for example, the number of pencils sold on day 1, x1, is Poisson with lambda equals 5. If we look back and remember what the properties of a Poisson distribution are, we will find that that means that the expected value of x1, which we could write as mu, works out to be lambda, or 5. And it turns out also that the variance of a Poisson random variable is also equal to lambda. So the variance, which we would call sigma squared, is also lambda, 5. So what this model for the number of pencils sold on one day tells us is that we know what the expected value and the standard deviation of the number sold will be. Now what we're really interested in is the number of pencils that we're going to have in stock for 30 days. So we're really interested in looking at a total of 30 random variables, the number of pencils sold on day 1, day 2, day 3, and so on. And we're interested in the total, which would be x1 plus x2 plus and so on up to x30. That would be the total number of pencils sold. Hopefully you can start to see how the central limit theorem might come in here. What we would like to be able to do is say, what is the distribution of this total? Because if we know that distribution, we can start to figure out probability statements about what the probability is that we exceed a certain number of sales in this 30-day period. That is, the sum of the sales over the 30 days exceeds something. And so we could use the central limit theorem in one of two forms. We might as well use the central limit theorem for the total here. It says that the total will be approximately normally distributed with expected value n mu and variance n sigma squared. Here we have n equals 30 days. And so what that means is that our total will be normally distributed with expected value 30 times 5 and variance 30 times 5 as well. That is, it's normal with expected value 150 and variance 150. Or equivalently, the standard deviation might be the square root of 150, which is about 12.24. So that's the same as saying sigma squared, the variance for the total equals 150, or equivalently, the standard deviation for the total would be the square root of 150, which is 12.25, roughly. All right, so now what we're asked is we want to find a number of pencils so that the chance of selling out will be 1%. So we want to find the probability that the total exceeds some number, let's call it A. We want that to be 0.01, and we need to find A. Equivalently, we could say that that's the same as the probability that t is less than or equal to A is 0.99. Now, we know from above what the distribution of t is by the central limit theorem. So we could say, okay, we know that t is normally distributed with expected value 150 and with standard deviation 12.25. So that's equivalent to saying that the probability that t minus 150 over 12 1/4 less than or equal to A minus 150 over 12 1/4 equals 99%. And the this thing here is going to be a standard normal. Because what we're doing is we're subtracting its expected value, 150, and we're dividing by its standard deviation, which is 12 1/4. So that is, we can say that the probability that a standard normal is less than or equal to something equals 0.99. Now, we know what this something should be for a standard normal. We can go look it up in our table, or we can use R. In R, we could simply type qnorm of 0.99, and when we do that, we would get 2.326. So we know that this value here is 2.326. And if you draw a standard normal, that will sort of make sense, because a standard normal looks something like this. This is 0, 2 is somewhere out here, and the chance that you're less than or equal to 2 is going to be some large number. So what we know then is that a minus 150 over 12 1/4 has to equal 2.326. And now all we have to do is solve for a. So what we can do here is we multiply both sides by 12 1/4 and add 150, and we would get that a equals 12.25 times 2.326. That's multiplying by 12 1/4 and then adding 150. And when we do that, we get 178.49. Or about 178 or 179 pencils. We could round up to be on the safe side. So even though we would expect the expected number of pencils sold in 30 days would be 150, we only need to have an extra 29 pencils on hand to protect against selling out, which is a surprisingly small amount. Basically, what's happening is that the central limit theorem is saying that on some days you may sell more, on other days you may sell less, but the amount of variability in the total will be predictable. And buying about 179 pencils should cover it.